Welcome to the video on aromatic compounds. Usually, when we think of the word aromatic, we think of a strong smell or a strong odor. Initially, this was the case, as the first aromatic compounds that were discovered did have a strong odor. Although it turns out now most aromatic compounds are actually odorless. And so, scientifically, what aromatic means is it has the proper number of pi electrons that contribute to a delocalized system. Benzene is the easiest example. Benzene has 6 pi electrons and it's in a ring, and so benzene is aromatic. Many of benzene derivatives are also aromatic because they have that core benzene ring involved. For example, toluene just has a methyl group off of benzene, and orthoxylene has 2 methyl groups off of the benzene ring. These are all aromatic compounds, and this chapter is going to delve deeper into what does it mean to be aromatic. Aromatic rings are everywhere. They're often in drug compounds as the ones shown here. They're also contained very frequently in coal. We have these fused benzene rings held together by these linkages. What's not mentioned here is that there's also aromatic compounds in our proteins and in our DNA. So nucleic acids and amino acids do have aromatic components as well. And so if we turn our attention to the structure of benzene, Kekulé proposed that benzene is a ring comprised of alternating double and single bonds. Here is double, single, double, single, double. And so this is a conjugated system. Kekulé realized that actually the ring could be written this way as well, where the double bonds alternate in the opposite pattern. He discovered actually the process of going back and forth between these two structures, and they're just resonance structures, is in an equilibrium. So if we have the double bond move here, and that double bond move here, and that double bond move here, we have a resonance structure that shows the double bonds in the other positions. And so if we measure the length of any one of those bonds, they would be about 1.5. So halfway in between a double bond and a single bond. So what we can imagine then instead is our resonance hybrid that has this situation, which ultimately gets abbreviated to this structure here. Now, what's so special about benzene is that it is incredibly stable. So stable. If we recall alkene reactions where we have a double bond and we add Br2 and we add anti to that double bond, so we have the trans product. Aromatic rings, even though they have a double bond, do not do addition. Aromatic rings do not undergo addition. In terms of the stability of benzene, heats of hydrogenation can be used to see that stability. When we have one double bond and we hydrogenate, the energy that's given off is shown here. When we have 2 double bonds, the energy is given off is here. If we continued in that same fashion and thought about the energy that would be required for 3 double bonds, we would expect that it increases and it's way up here. In actuality, however, the energy in terms of the heat of hydrogenation is much lower than what is expected. This is observed, which indicates that our benzene ring itself is more stable than simply having 3 independent double bonds. And so there's this added stability that comes from benzene. It's more stable than expected. So heat of hydrogenation tells us that benzene is more stable than expected. It turns out that not all of the fully conjugated rings have this aromatic stability. Cyclobutadiene is not as stable as benzene. Cyclooctatetraene also does not have that stability. As a matter of fact, when we take cyclooctatetraene and react it with Br2, we do get addition. Benzene is stable because it is aromatic. In order for a compound to be aromatic, it has to meet 2 criteria. The first one is that it has to be a fully conjugated ring with overlapping p orbitals. So we have to have a ring that is fully conjugated. So it cannot contain an sp3 hybridized carbon. The second criteria is that it has to follow Huckel's rule. And Huckel's rule says that we need an odd number of electron pairs, or that we follow 4n plus 2. So we take 4n plus 2 and set that equal to the total number of pi electrons we have in our system. Solve that equation for n, and n equals a whole number, 0, 1, 2, 3, 4, etc., then we are aromatic and we have followed Huckel's rule. The following two compounds do not meet Huckel's rule. They are fully conjugated rings with overlapping p orbitals, so they do fit criteria 1, but criteria 2 does not work. For example, if we have 4n plus 2 equals 1, 2, 3, 4 equals 4, subtract 2, 4n equals 2, n equals 1/2. That is not a whole number, therefore it is not aromatic. Same here, 4n plus 2 equals 8, 4n equals 6, n equals 1.5. That is not a whole number, and so this one is not aromatic. Benzene, on the other hand, if we calculated Huckel's rule for benzene, 4n plus 2 equals 6, minus 2, minus 2, 4n equals 4, n equals 1. Yes, benzene is aromatic. So benzene is not the only aromatic compound. Again, in order to be aromatic, we need a fully conjugated ring system with overlapping p orbitals, and we need to meet Huckel's rule, right? 4n plus 2. N has to be a whole number. Anti-aromatic compounds have to fulfill two criteria as well. This one needs to be fully conjugated ring with overlapping p orbitals, so that's the same as aromatic. And in this case, we need to have an even number of electron pairs. And so this equation we're going to use is 4n equals the number of pi electrons that you have. And if n equals a whole number here, then we have anti-aromatic compounds. If a compound fails criteria number 1, it is called non-aromatic. So annulenes are compounds that have conjugation. This has 6 pi electrons, 1, 2, 3, 4, 5, 6. And so this one is, we've determined, aromatic. This one has 10 pi electrons, so 4n plus 2 equals 10. It turns out with 10, we actually are aromatic as well. And 14 would follow the same suit. 4n plus 2 equals 14. Here n equals 2, and here n equals 3. And so those are all aromatic compounds. Another way to think about aromatic compounds is a compound that has an odd number of pairs of pi electrons. We're going to talk about aromatic rings that contain carbanions or carbocations. Consider the 5-membered ring, cyclopentadiene. Remember, we have to have 6 pi electrons present in order for it to be aromatic. So if we think about this species right here, in order to get 6 pi electrons, we actually need an anion. So let's take a look at cyclopentadiene anion. If we count up the number of pi electrons, or maybe now we'll talk about the number of electrons that are delocalized, we have 1, 2, 3, 4, 5, 6. That lone pair on the carbanion, remember what a carbanion looks like, right? So we have that lone pair up in that sp3 hybridized orbital, and it can be delocalized. And so this compound right here, because it has 6 pi electrons, 4n plus 2 equals 6, n equals 1, this compound right here is aromatic. If we draw all 5 of the resonance structures of cyclopentadienyl anion, we see that that negative charge moves and it hits every single one of the 5 carbons. So not only is the charge completely delocalized, but we also have n equals 1, so we have this aromatic distinction. If we think about the fact that the pKa of that sp3 hybridized CH in the anion of cyclopentadiene is 16. A typical alkane, remember, is 50, but here this is 16. That is because when that conjugate base is formed, it is highly stable, not only by resonance, but by being aromatic. So if we're thinking about a 7-membered ring, that already has 6 pi electrons. What we need here is an empty p orbital. So we need a carbocation at that position, so we can then have an aromatic system. And that's exactly what happens. As we look at that carbocation, we have 7 resonance structures. Each one of them has a positive charge on a different carbon, and all 7 carbons share that positive charge. And with this empty p orbital, this is no longer an sp3 hybridized carbon that gets in the way or blocks this delocalization. Instead, that empty p orbital allows the electron density to be shared throughout the whole ring, making that an aromatic compound. And lastly, we can have heteroatoms in our aromatic compounds as well. For example, if we have nitrogen, remember nitrogen always has a lone pair. And so it turns out when nitrogen is sp2 hybridized, then those electrons are out to the side in an sp2 hybridized orbital that's planar. Those do not contribute. And so pyridine has these 6 pi electrons here that make it aromatic. However, in pyrrole, because nitrogen now is sp3 hybridized, those lone pairs are put right up in an sp3 hybridized orbital. Those actually contribute. And so now we have 6 pi electrons here as well. And it's shown also nicely down here when it's sp2 hybridized, those lone pairs are off to the side and do not contribute to the delocalization, whereas when it's sp3 hybridized, those electrons are right up in the sp3 hybridized orbital and they contribute in the delocalization. We can look at the pKa's of some of these compounds too. For this compound right here, which is aromatic, if this nitrogen is acting as a base and it becomes protonated, it's still aromatic. That is going to be a weaker acid and a stronger base. However, in the bottom example with pyrrole, when that nitrogen gets protonated and becomes this positive charge here, that is no longer aromatic. And so that is going to be a very strong acid and a weaker or much more stable base. A pKa of 5.2 means that we have a weaker acid but a stronger base. Whereas in this situation down here, a pKa of 0.4 means that we have a very strong acid, meaning that it prefers to be in the base form, meaning that this is going to be a weak base. Stronger base up here and a weaker base down here. We can use electrostatic potential maps as well. We see here that in pyridine, that lone pair is very localized in that one position where the nitrogen is. And in pyrrole, we see that it's delocalized around the whole ring. We can also have aromatic compounds that have fused benzene rings. And here are 3 examples. There you have it, aromatic compounds and an introduction to this amazing compound called benzene.